Okay, so we had left off with the comparison test. So let's talk about some more comparison test examples. And then you guys worked on the alternating series test yesterday and looked at alternating series yesterday in recitation. So we'll just briefly review that. And then we'll move on to the ratio test and absolute convergence. So let's see, we can pass by this. So we know the idea of the comparison test. If you have, we talked about convergence, a series that you are given, you can conclude as convergent. Or sorry, if you're given the series, say the sum of terms A. If there's another known series that converges and all of its terms are bigger than the terms of yours, then you can conclude yours as converges. On the flip side of that, if you're asked to find a series and you have another series that diverges and all of its terms are less than, or all of your terms are greater than this series that diverges, then you can conclude that yours diverges. Okay? And so let's look at, so we looked at that example last time. Let's look at this example now. So what do I have? I have 3 over, I have 3 over radical I minus 2 cube root of radical I. So what can we compare that to? Let's take a look at, let's start by looking at 3 over radical I. So what can we say about this series? What kind of series is it? Does it converge or diverge?
Series and modulus.
So is this geometric? Is it a p-series? Is it something else?
P-series.
P-series with p equal to?
1/2.
1/2, which is less than 1, therefore?
It diverges.
Diverges, right? The p-series converges when p is greater than 1, right? The harmonic series is like the last one that still diverges. P equals 1. And then as soon as you get greater than 1, then those series converge. But this is less than 1, so it diverges. And so then how do these terms compare? So this is the one we're analyzing. How do the terms of this series compare with this one?
They're less than.
Okay, so what do we think? We're going to make the denominator smaller. If we make the denominator smaller, does this become larger or smaller than that? Okay, you should be thinking larger, right? So if the denominator is smaller, right? So it's the same thing but minus a little, some positive value. That denominator is smaller, then that whole ratio will be larger than that. And what do we say about this one? When you add up all these terms, it diverges, and now we have a bunch of terms that are all greater than those terms. Conclusion? For every I
Diverges.
and diverges, then also diverges. Okay, so for every term we have the one that we're analyzing, every term is greater than terms of a series that diverges. So that would make sense then, since this is bigger. It's bigger than something diverging, so therefore this also diverges. And this is called direct comparison. This is direct comparison. Or just comparison. Does this make sense? Does this example make sense? Any questions on this?
how do you know which sequence to compare the other sequence to?
So we want to compare it to something that we know like kind of readily, right? Like so a P series or a geometric series. So the obvious choice here is this P series right here. And then we know that subtracting from the denominator makes all terms larger than that. Does that answer it? So we're looking for some P series or geometric series usually that's really close to the one that we're given.
Yes, thank you.
Okay, sure. Okay, so now what if this one was alternating? What if I changed this problem and I made it -3 to the I, which would be like -1 to the I. No, that's not right. Can't do that. So I need to just do -1 to the I. So new problem now. So new problem, -1 to the I. What about this series? So what was our alternating series? So first of all, and I should have said this before. The first test we always look at is the divergence test. And I should have done that. Always consider the divergence test. What is that? If this sequence does not go to 0, then we're done. If it doesn't go to 0, what can we say about the series?
It won't
Converge.
converge.
It diverges. That's the only chance that a series has to converge is if the sequence goes to 0. So if it doesn't go to 0, does anything else but go to 0, then it's like game over. Just stop. The series cannot converge. So this certainly goes to 0, right? So certainly this goes to 0 because we have a big denominator, and we should have done that before we used the comparison test, but that's okay. So it goes to 0. Then we use the comparison test to find out that it diverges because all the terms are bigger than a series that diverges. But now this thing alternates. So now it alternates. So it still goes to 0. And so what can we say? Converge or diverge?
It converges.
Okay? And so what did the alternating series test said? It said that if you have a series that alternates and the terms, the positive part of the terms so the positive part, which was the original part that we have, if those are decreasing and going to 0, right? So if that's a decreasing, so if 3 over is decreasing, positive, decreasing, and goes to 0, then as long as it doesn't matter how slow it goes, right? So it doesn't matter how slow this thing goes to 0. All that's required now is that it goes to 0. Not that it goes to 0 fast enough, but just that it goes to 0 if it has the alternating effect on it. So this thing without the alternating, it diverges, right? Because it goes to 0 too slow. But you put the alternating effect on it, as long as it goes to 0, that's all that is required. It doesn't have to go to 0 fast enough anymore, just at any rate. So it's just as long as this part is positive, decreasing, and decreasing to 0, along with the alternating effect, it will converge. That's what the alternating series test says. Questions on that?
Professor Asper?
Yeah.
Oh, I have a quick question. So if without it alternating for the second series,
Right.
it would not converge.
That was the one we did before by comparison. Yeah,
Yeah.
that was the problem we did just prior to this by comparison. It diverges essentially because this is like a P series with 1/2.
Okay.
Yeah, so that was the previous problem. We showed it diverges by comparison to 3 over radical I. But make it alternate, and now this series converges by the alternating series test. Because all this needs to do, the positive part, all it needs to do is decrease and get close to 0, or go to 0. Okay. Any other questions about that one?
I
Right.
have one question.
Yeah.
Why is it that you say like it has to be positive? What does that mean?
So it's just part of the test that the non-alternating part is positive and going to 0. All those terms are positive. So this part of it. Because if this part alternated also, like, and it alternated opposite to this, then all the terms would be positive, wouldn't actually be alternating at all. Does that make sense?
Okay.
Like if this went negative, if this part of it alternated and then you multiplied it by this, then the whole thing might not alternate anymore.
Okay. Yeah. That makes
So
sense.
that assures that we have an alternating sequence. If this is all positive and then we have the alternating factor on there.
Okay.
Okay, next example. This one. So here I got 5 to the j minus 1 over j times 2 to the 3j. What do we think about this? Well, we see two different things here. We kind of see like the harmonic series in there, like kind of 1 over j, and then you also see this geometric part to it. So, you know, if we're focusing on the harmonic series, then we would be trying to prove this thing diverges. If we're focusing on the geometric part, then we got to see what is our ratio? Is it less than 1 or greater than 1? So what is if we separate this thing out? So we kind of have to just kind of work at this and see what's gonna work. So I'm going to separate out the kind of one that looks kind of like harmonic, and then I got 5 to the j minus 1 over, now I've got 2 to the 3j. So I really want that to look like 2 to the j or 2 to the j minus 1. So what value is it to the j? So
8.
8, right? So 2 to the 3j is like 8 to the j. So now I look at this. What do I have? I have a geometric series, and we could get them to both look like j minus 1. That's no problem. But I have a geometric series, and what's my r value?
5 over 8.
Yeah, really my r value is going to be 5 or 8, less than 1. So what will that do? That's that, as just a geometric series by itself, converges. And then what does 1 over j do to all the terms of that geometric series, multiplying by 1 over j? Make them bigger or smaller?
Smaller.
Smaller, like 1/10, 1/11, 1/100th, 1/200th. So this is going to make all my terms of my geometric series smaller. And this geometric series converges. Therefore, converges by comparison to geometric series with r equals 5/8. Does that make sense? All these terms will be smaller than all the terms of a geometric series with an r of 5/8 because we're multiplying those terms by 1 over j, makes them smaller. And so we have a series that converges. Our series has all terms that are smaller. Therefore, our series converges also. Questions on that one?
I have a question.
Yeah, sure.
Does the harmonic part have any rules at all?
Yeah, it makes the terms smaller. That's what we said. We're comparing
Oh,
it
it
to.
just makes it okay.
Yeah, that's what's making all the terms smaller than our geometric series with r equals 5/8. by multiplying by 1 over j. Other questions?
So if a geometric series has basically a limit or converges to less than 1, then
No, if
the
r is less than
I mean,
if r is less than 1, then the geometric series converges. It doesn't converge to the r value. But anyway, go ahead.
oh, okay, that explains it.
Yeah. So
Because
we noticed that r was 5/8. That means that the series converges to a over 1 minus r, if it's a pure geometric series.
okay,
If r is between 1 and -1. That was our geometric series conclusion.
thank you.
Okay. All right, this last one. So this last one, okay, so we look at this and we say, oh, this is like a p series, 1 over k to the 4th. How do all these terms compare to say, how do they compare to 1 over 3k to the 4th? Are all these terms bigger or smaller than 1 over 3k to the 4th? Bigger. Smaller denominator means a bigger value, right? We're reducing the denominator. So look, I've got a p series that converges, and all my terms are bigger than that. What's the conclusion?
Doesn't prove anything.
Right. So that should make sense. If this converges and I have a bunch of terms that are bigger than the terms of a series that converges, there being no conclusion by direct comparison. Okay? But what we can do is we can think about this as a rational function and think about, okay, what's going to happen when k gets really, really large? So as k gets big, 1 over 3k to the 4th minus k cubed minus k does what? It becomes like 1 over 3k to the 4th. So in the end, so when k gets really large, these terms really don't kind of matter anymore. And this thing gets very, very similar to 1 over 3k to the 4th, which converges. So although we can't conclude it converges by direct comparison because the terms are all bigger than this, we use something called what's called limit comparison. So therefore, this one does converge because it virtually ends up like this in the end, in the limit, right? So therefore, the series converges by what's called limit comparison. So I know this is a little bit weird. It's like we did direct comparison. We say, oh, we can't really conclude anything. So then we can look at, okay, so what happens when this just gets really, 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 k's get really big? Well, this thing essentially is 1 over 3k to the 4th in the end. So that's the reasoning of limit comparison. So we can say this, even though these terms are a little bit bigger than these, it still will converge because in the end it's still essentially 1 over 3k to the 4th. And that's called limit comparison. Okay, questions on that? Does that make sense? Okay.
I have a question.
Sure, please.
So will we do direct comparison, and if it doesn't work, then we do limit comparison?
That's often that will work. Yeah. So always look for direct comparison first. It kind of feels like a little bit stronger, right? Like direct comparison. It's like, look, every single term is bigger, and we know this other one diverges, and every one of my terms is bigger. So it's like it's kind of this feels a little bit like stronger, more conclusive. So use direct comparison when you can. But if there's no conclusion, then we can use limit comparison, which is still completely valid, right? So it's completely valid. It's just it doesn't have that strength of like, okay, every term is less, therefore mine converges. But it's still completely valid.
Okay, thank you.
You're welcome. All right, so let's move on. So that was some examples of the comparison test, that direct comparison and then limit comparison. All right, so you guys worked on that yesterday. So this is to review the alternating series test. So the alternating series test said that you have an alternating series, and if it's decreasing, this says it's decreasing. And so I should have also included that all the BIs are positive, right? So if your BIs are positive, and how can we do that? We can do this by saying that these are greater than 0. So all the B's are 0 and it's decreased, or all the B's are positive and it's decreasing. The next one's always less than the one before. And that thing goes to 0. That's all that's required if it alternates. And then you can conclude that the series converges. So I think you guys did these in recitation yesterday. Did these natural log examples?
Yeah.
Great. Okay. So let's talk about a new concept called absolute convergence. Absolute convergence is, here's the idea. Does the series require the alternating help in order for it to converge? So we saw like with the harmonic series. The harmonic series diverges, but then when you make it alternate, like you found out in recitation, then it converges. So it like kind of requires that alternating help to get it to converge. If it doesn't have the alternating help, it diverges. So does it require the help? Or does the series just converge whether or not some of the terms are negative? So regardless of whether it alternates or not, does it still converge? Okay, so this choice B here is the idea of absolute convergence. That if a series converges whether or not it alternates, it does not need the help of some terms being negative, then we say the series converges absolutely. So mathematically, what would that be? It would be, we say that a series converges absolutely if the absolute value of all the terms also converges. Meaning, get rid of all the negative terms and see if all the positive versions of the terms, if that converges, then it converges absolutely. If this converges, but this one doesn't, that's case A, where you need the alternating help, and that's called conditional convergence. So an alternating series converges conditionally if the series converges, but not absolutely. In other words, it needs the alternating help to converge. Okay, so does the premise make sense? At least a little bit. So I think a couple examples will help. Right, so the most obvious example is the harmonic series and the alternating harmonic series. Harmonic series, does it converge or diverge?
Diverge.
Diverges. We showed that a couple classes ago, that this goes to 0 but not fast enough, right? It goes to 0 but not fast enough. Well, what about the alternating harmonic series? Converge or diverge?
Converge.
That converges. When you make every other term negative, this is going to be tremendously helpful to get this sum to add up to a finite number, right? It should make sense. If you add up all positive values, it gets really big. But now if you take every other term and make it negative, well, then you're going up and then down a little, and then up and then down a little, and then up and then down a little in your partial sums. So this one converges. Now, does it converge absolutely or conditionally? Meaning conditionally, because if you take the absolute value of all these terms, then you've got the harmonic series, and it does not converge. So this is conditional convergence because it's dependent on requiring the alternating effect to get it to converge. So that's the most obvious example. So what about this? So let's look at the alternating P series just in general. For what values of P will the series converge absolutely, conditionally, or diverge? So here's a couple examples. So here's the alternating P series with P equal to 4. Does it converge absolutely?
Yes.
Why?
Because without the alternating component, it would converge anyway because p is greater than 1.
Oh, well said. That was excellent. So this converges absolutely. Why? Because take off the alternating, take the absolute value of all these, or just, and it still converges. Does it make sense? So the alternating P series with, say, P equals to 4 converges absolutely, because if you take off the alternating effect, it still converges. Okay, how about this one? So here I have 1 over the cube root of j, which is 1 over j to the 1/3. First of all, does it converge? Does this converge? And by what reasoning does this series converge?
It converges because of the alternating help.
Right, alternating series test, right? These are positive terms decreasing to 0, and it alternates, therefore converges by alternating series test. All right, the question is, does it converge absolutely or conditionally?
Conditionally?
It will right, because now if we take the alternating help off, we have a P series with P what? Less than 1. And if P is less than 1, then it will not converge. It only converges conditionally, on the condition that we have the alternating help. This diverges because P is equal to 1/3, which is less than 1. Okay, questions on those? Okay. Let's look at a geometric series in the light of absolute convergence. So here's one. Before we look at this, so what if R is positive? If R is greater than 0, and less than 1, of course, then what can we say? What would all the terms would be what?
Converges absolutely.
Yeah, so all the terms are positive. it doesn't alternate. And we know that we'll get it, when r is less than 1, this converges. And with all positive terms, it will converge absolutely. Okay, so now,
But if it's, then we wouldn't be able to use the alternating series test, right?
what's that?
If r is negative, then we wouldn't be able to use the alternating series test, right?
Well, we wouldn't need the alternating series test because we are analyzing it as a geometric series. I mean, we could, but we could use the alternating series test if r is negative because it will alternate, but we don't need to because we know the facts about geometric series without knowing the alternating series test. Does that make sense?
Yeah, I was saying if it's alternating and r is negative.
Well, that's just going to, well, if r is negative, that makes it alternate. So
Right.
if you also put an alternating term on, it'll still be alternating. It'll just be the pluses and minuses will be flipped.
Okay.
So that won't really affect anything. Okay. So this is the more interesting case. So r is less than 0. So r is between, like this one. So here r is negative 2/5. What can we say? So does this series converge?
Yes.
Yes, because r is between 1 and negative 1. Does it converge? Absolutely. So what happens if we put absolute value bars around this series?
It wouldn't change anything.
It's just gonna, what's it gonna do? It's gonna make r equal to positive 2/5. Does that converge?
Yeah.
Yeah. Because right, so put absolute values bars around it, take off the negative, the alternating effect, which is essentially making r equal to positive 2/5. Well, that still converges. So what's the conclusion? All geometric series that converge absolutely. So these geometric series, they go to 0 fast. They do not need, if r is between negative 1 and 1, they will get to 0 fast enough, regardless of having a negative alternating effect or not. All geometric series that converge are also absolutely convergent. Does that make sense? Okay, so we have a test for, so we kind of have been testing so far. We've been looking at absolute convergence in terms of the definition. You know, make all the terms positive and see what happens. Well, there's a test for some more complicated sequences to test for absolute convergence, and that's called the ratio test. Okay, so here's what this is. We've got our series, and we set up a new sequence. Okay, we set up a sequence of the ratio of one term to the previous term. So we can make a bunch of ratios out of consecutive terms by taking the next term divided by the previous term and make a sequence out of that. And then we're going to look at the limit of that sequence. This should be I. Okay, we're going to look at the limit of that sequence, and the limit of that sequence is going to tell us if the series converges absolutely diverges, or it may yield no conclusion if that limit is 1. Okay, so before we get into the rules, let's talk about what's going on here. So this is important. Here's remember the geometric series, AR to the I minus 1. So let's put an I. What's going on? Gee whiz. Here we go. Okay, AR to the I minus 1. That was our geometric series, right? And so what did we say? How do we always get the next term in a geometric sequence or geometric series? What does it take to get to the next term? What are we doing?
Multiply.
Multiplying by another r.
By r, right? We always, to get the next term, you just always keep multiplying by another r. That's why it's r to the I. Right? You just keep multiplying by another r. So in just any generic sequence, so this a is not this a. This a is the coefficient in our geometric series. This is just a generic sequence. What would be the multiplier to get to the next term? So like what would you multiply a1 by to get a2? And what would you multiply a3 by to get a4? So for instance, a1 times x times a1 gives you a2. What's x? What number do you multiply a1 by to get a2? Solve for x.
R.
No, just solve this for x.
A2 over A1.
A2 over A1, right? You'd multiply by A2 over A1 times A1 would give you A2. Similarly, A2 times A3 over A2 would give you A3. So how would we get the n plus first term from the a nth term? We multiply by what? The ratio of the next term to the previous, right? If we multiply an times the ratio of an plus 1 to an, we get an plus 1. So this ratio right here is like, it's like what?
Geometric.
It's like r. It's like the value of r. The difference is it could change, right? So with a geometric series, that r stays the same for every, as you go. Here, these ratios are changing, right? These ratios, a2 over a1 could be different than a3 over a2. And so every ratio could be different. But in the limit, if this thing in the limit goes to L less than 1 as I gets large, then what can we say? We can say that that ratio is approaching a value less than 1. Well, that's like r. And if r is less than 1, what do we know? If r is less than 1.
It converges.
It converges, right? So a geometric series has a constant r, and if r is less than 1, it converges. The ratio test is looking at the sequence of these ratios and saying, like, what if that ratio becomes like an r value? It gets closer and closer to an r value that's less than 1. If that ratio gets closer and closer to a value less than 1, well then what? This is becoming like a geometric series with that r value. And if this ratio is, the limit of this ratio is getting closer and closer to a value greater than 1, well, then it's becoming like a series with that, like a geometric series with that r value being greater than 1. And it would diverge. That's what this is saying, right? Look at the limit of the sequence, which is something like the multipliers, like r. And if those multipliers converge on a value that's less than 1, well, then this sequence is becoming like a geometric sequence with r less than 1. And if those multipliers, those ratios, are converging on a value greater than 1, well, then this is like a sequence with r, like a geometric sequence, or becoming like a geometric sequence with r greater than 1, and we'll diverge. Does it make sense? So the ratio test is testing to see if your sequence is becoming like a geometric sequence where either r is less than 1 or r is greater than 1. And if it's equal to 1, there's no conclusion. We need a different test. Okay, does the premise make sense? All right, so let's do a couple examples. We got 3 minutes left. Okay, so here's one. So what do we need to do? We need to set up this sequence. So given this is the jth term, we need to set up this ratio, which is a sequence, and take its limit. So here we go. So I need, since it's j, I need a j plus 1 over a j, and the absolute value of that. Okay, so what is a j plus 1? Well, that would be negative 3 to the j plus 1 over j plus 1 cubed. That's the j plus first term of this over the jth term, which is just this. So here's the j plus first term of that sequence. Here's the jth term of that sequence. So I'm dividing two fractions, so I can invert and multiply. So I'm going to invert and multiply, so I'll have negative 3 to the j plus 1 over j plus 1 cubed times j cubed over negative 3 to the j. And so when you use the ratio test, you can start here. You don't have to do this step if you don't want. You can just do a to the j plus 1 times the reciprocal of aj, just to save writing. So if you want to start with this step, that's perfectly fine. But know that it comes from the ratio. All right, so now we can...
Where did the j plus 1 cube come from?
This. Right? I'm doing... this is the j plus first... The j plus first term of the sequence would be negative 3 to the j over j plus 1 cubed. Do you follow that?
Oh, okay, I see.
Yeah, so it's going to be just everywhere there's a j, now you're going to have j plus 1. Okay, so then what do we have? We're going to have, we can combine our like things, right? So this says I have j plus 1 negative 3's. Here I have j negative 3's. So I have one more negative 3 on the top. And then I have j cubed over j plus 1 cubed. And so now we have to go back to our limits of sequences, right? Limits of sequences. What's the limit of this sequence? So we got j cubed over j cubed plus other stuff. So that, because those have the same degree, that will go to 1, right? It'll go to the ratio of the coefficients, 1 over 1. And then I'll have also times this negative 3, but then it's absolute value. So this goes to 3 as j goes to infinity. Therefore, and 3 is greater than 1. We got this condition here. So this diverges by the ratio test. So what does this tell us? What does this number 3 tell us about this series? Here's the big point. This is the most important thing. What does this number 3 tell us about this series? Anybody?
Series diverges because the limit of like the change between each value in the series is greater than 1, so that means that each change is making it increasingly larger instead of smaller if n
Okay.
is less than 1.
Okay, good. Yeah, that's right. And what is this? Can we compare? What can we kind of compare the series to? Based on the fact that we got this to be 3, what can we say about this series? What is it like? Or what is it becoming like? Remember, this sequence was like the multiplier from one term to the next. And so the limit on the multipliers on this sequence is 3. So in the very end, it's like we keep multiplying by 3 each time. What is that? So what is that like?
A geometric series?
Right. So the fact that we get a 3 here, 3 is the multiplier, means that this series is like becoming, in the end, it's becoming like a geometric series with r equals 3. So the multiplier will keep changing from term to term, but that multiplier will get closer and closer and closer to 3. And if it gets closer and closer to 3, it's like this thing is becoming geometric with an r value of 3. And so we know that diverges because r is greater than 1 then.